Welcome to session number 33. In today's session, we're going to be continuing our discussion on the metal oxide semiconductor structure, the MOS. Specifically, we're going to be looking at things like effects of doping and oxide thicknesses on the structural performance. And then we'll be going into some numerical examples from Chapter 19, which is a chapter on work problems. And finally, we'll be starting to Chapter 18, which is corrections to the simple model. Chapter 17, we looked at the MOS structure more or less qualitatively, and we consider things like reconversion not in its full glory, but in Chapter 18, we look at the more mathematical structure. And there's going to be a fair amount of mathematics. Hopefully it won't be too painful. But before we get started, I'd like to share with you a wonderful performance of the song Danny Boy, and we'll see you in about 3 minutes.
I'll just tell you something about this next song. It's a song that was first sung in Ireland by a man who had 3 sons. The eldest 2 have both been killed in the war, and now his 3rd son is leaving home. It's a song which will mean a great deal to anyone who has experienced the heartache of being parted from loved ones. It's the story of Danny Boy. Oh, Danny Boy, the pipes are calling from glen to glen and down the mountainside. The summer's gone and all the roses falling. It's you must go and I must bide. But come ye back when summer's in the meadow and all the valleys hushed and white with snow. I'll be here in sunshine or in shadow. Oh, Danny boy, I love you so. But when ye come and all the flowers are dying, if I am dead, as dead I well may be, you'll come and find where I am lying. I shall sleep in peace until you come to
Okay, so this is a rough outline of some of the topics we'll be covering today. We're going to start with the effect of doping on the metal oxide semiconductor device structure, look at gate oxide thickness, then we'll have a table of different types of semiconductor structures, and well, there's the Schottky, the metal semiconductor, the PN junction, and the MOS, and we'll compare those in a number of different parameters. Then we will look at some problems, work problems from Chapter 19. Chapter 19 is a chapter which only includes work problems in the MOS structure. And then we'll go on to Chapter 18, which will look at the corrections to the simple model. I maybe should have put that in quotes here. What we've been doing right now is, quote unquote, the simple model. We haven't looked at the full mathematical complexity. So we'll try to do that in Chapter 18, and hopefully that won't be too difficult. We'll get through it. And then finally, we'll look at a video clip, very powerful clip from the marvelous movie, I believe it was 1940 or 41, The Grapes of Wrath, with Henry Fonda. Okay, so let's get started with the effect of doping. So here's our reasoning. We started with moderate doping of 10 to the 16th. I think the three nice kind of middle dopings we'll be looking at is 10 to the 15th, considered light, 10 to the 16th, considered moderate, 10 to the 17th, considered, well, moderate to heavy. Okay, so if we reason that if we go to 10 to the 15th, a light doping, where the Fermi level is much closer to intrinsic, we don't have that far to invert. So we would reason that the threshold voltage would decrease. And, well, we have a little bit of a problem there, because we saw previously that we had a higher doping and we had a lower threshold voltage. So that seems to contradict what our intuition would tell us. Our intuition says that as we go down in doping, the threshold voltage should be lower. Our results seem to contradict that. Well, here's the rationale, or here's the reason, or the resolution. And it's a rather simple resolution. Previously, the one with the lower threshold voltage, we were talking about a very thin gate oxide, whereas in the present, the case where we just discussed here with the 10 to the 16th, we were talking about a extremely thick gate oxide. And the thicker the gate oxide, the less control the gate has over the silicon, and therefore the more voltage we have to apply. Threshold voltage, in fact, is lower in the lower doping if the gate oxide remains either high or low. So that's the idea here. All things being equal, gate oxide has a much bigger effect on threshold than even the doping. So let's go back to our original formula for the amount of band bending in the silicon. And if we didn't do this previously, I'll do it right here. If we have a flat band equal to gate voltage equal to 0, no flat band at equilibrium, which is gate voltage equal to 0, we would expect no band bending. And that's exactly what we see here. Because if VG and VB are equal to 0, this goes out and 1 minus 1, and the whole thing collapses to 0. Or if we have a finite flat band voltage, but the gate voltage is equal to that flat band voltage, the same thing happens. That's the definition of flat band voltage. When the gate voltage is equal to the flat band voltage, then there is no band bending. Okay, we're going to start with, we're going to keep the flat band voltage at 0, but we're going to go to a gate voltage of 1 volt. So in the parentheses here, we have 1, and we find that the band bending is 0.61 volts dropped across the silicon, and therefore, since we have 1 volt total dropped from the gate to the bulk silicon, we must have the remainder, which is about 0.4 volts dropped across the oxide. And we go with 2 volts, we find that the numbers work out to be 0.68, a little bit increase, and 1.3 volts is dropped across the oxide. The distribution is not particularly sensitive to gate voltage in depletion. Most of the voltage is dropped across the oxide, and that's because the gate oxide is quite thick, about 1,000 angstroms. So the distribution, the relative distribution, is unchanged. The threshold voltage is 1 volt. So in this particular case, we are in depletion, maybe close to weak inversion. And again, all of that is for a light doping here. And I can see I made a mistake here. This should be 10 to the plus 15th. So you can correct that. But the numbers work out, I believe, correctly. So finally, we consider a heavy doping of 10 to the 17th. And we put in the same numbers, gate voltage of 1 volt, gate voltage of 2 volts. Again, the gate oxide is quite thick, at 1,000 angstroms. But we notice something rather interesting here for the heavy doping. Look at the drops across the silicon, the phi sub s, 0.036 for 1 volt and 1.3 volts, 1.36 volts for 2 volts. Especially for the 1 volt, it is minuscule compared to the 0.6. So we're dropping much less voltage across the silicon for the heavy doping than we do for the light doping. And why should that be? Oh, one more thing we should calculate before we go explain that. The threshold voltage is huge. It went from 1 volt, it catapulted itself up to almost 5.5 volts. And again, that is indicative of the fact that for the heavy doping, Fermi level is far away from intrinsic, 0.42 eV, rather than the 0.3 eV for the light doping. We have much further to go to invert substrate. And that's why the threshold voltage is so low. Why is there so little voltage dropped across the silicon for the heavy doping? Well, it's because the resistivity. The resistivity at heavy doping is much lower, and therefore voltage is always dropped. If you have two things in series, in this case the oxide and the silicon, we'll find that the predominant voltage is dropped across the high resistivity, and that's why there's so little band bending in the silicon at relatively low gate voltages. And finally, we look at the effect of the gate oxide. This is the predominant factor. Gate oxide is extremely important. We want to make it as small as possible so that the gate has maximum influence over the silicon substrates. So here we have a table for large gate oxide, 1,000 angstroms or 100 nanometers, with extremely small areal capacitance. and we look at the numbers for the gate voltage of 1 volt and a gate voltage of 2 volts, threshold voltages tend to be extremely high, lower for low doping, much higher for higher doping, and I've just indicated here the 2 times the bulk value. The bulk value for 10 to the 15th is 0.3, 0.36 for 10 to the 16th, and 0.42 for 10 to the 17th, each an increase of 60 millivolts, or 2 times that would be 120 millivolts. And now for the smaller gate oxide, this is moderate, still a little bit on the high side, but we look at these values, again the same trend as we go up in doping, the threshold voltage gets larger, and as we go up in doping, the oxide voltage drop gets larger, and the band bending across the silicon gets smaller due to the lower resistivity at the higher values of doping. And I've also indicated what we kind of feel this structure should be in. Remember, there are 4 different kinds of conditions. There's the accumulation, there is the depletion, there's weak inversion, and there's strong inversion. And because, well, we kind of feel that the threshold voltage, well, it's greater than the band bending, so we think this is probably in either depletion close to intrinsic, close to the point where the Fermi level and the intrinsic value cross, and it may be in weak inversion. This is even more so. We expect that this is probably weak inversion. This is less so, excuse me, went the wrong way. This is probably weak inversion. I should say this is possibly weak inversion. So let me correct that. Possible weak inversion. Because the threshold voltage is quite a bit above the band bending, and this guy is almost certainly in depletion. We have a very high threshold voltage, and we're not even close. But it is certainly in depletion because the flat band voltage in all of these cases is 0. And let's explore that a little bit further by keeping the doping heavy, moderate to heavy. But instead of having flat band voltage of 0, we have flat band voltage of minus 1 volt. And that is the quote-unquote normal situation. We have degenerately doped gate, N++ gate, and therefore the flat band voltage will be negative, about 1 volt, because the work function in the gate metal, also known as degenerately doped N+ silicon, is about 1 volt closer to the E0 level than the silicon substrate. So this is the new condition. Now we're going to go with an extremely thin oxide, and we're going to basically do the same thing. We start at equilibrium, gate voltage of 0. However, the flat band voltage is minus 1 volt, so the thing in parentheses reduces to 1 volt, and let's see, this should be 5.6 for gate oxide. So let me correct that. Well, I'll correct it later. Okay, so instead of 5, comma 6, it's 5.6 and 10 to the minus 12. Extremely large compared to what we had previously. We get a band bending of 0.9 volts. Really, really a lot of band bending. So even at 1 volt, we didn't have nearly that much band bending. The threshold voltage is 0.93 volts under these conditions, so we would expect this thing to be pretty much in strong inversion. And just one more example, if we go to a moderate doping, we would expect the band bending to go even higher because the resistivity is higher, and it does. It jumps about 10%. The threshold voltage goes down, and if there was any doubt here, there is no doubt here. This guy is in strong inversion even at equilibrium, and that is really a big deal. This structure then has a channel. It has a conductive channel at the surface, even though there is no gate voltage. So at equilibrium, the channel is conductive. This channel, or this structure, is referred to as a normally on structure. No gate voltage, we can still get a conductive channel, and we'll have lots more to say about that when we talk about the field effect transistor. So finally, in this section, let's take a look at some semiconductor structures. This should be table 17 for. I have a number of corrections to make rather than 7.14. So the metal semiconductor structure, we have a barrier. If it is rectifying, not all metal semiconductors are rectifying, but it can be either rectifying or ohmic, depending on the work function difference. The silicon surface cannot go beyond intrinsic. It cannot even approach intrinsic as we go to forward bias. In a rectifying junction, the external bias effect on junctions changes from conducting to non-conducting, whether we go from forward bias or to reverse bias, and of course inversion is not possible. In p-n junction, always rectifying, unlike the Schottky barrier. There is the metallurgical junction is always intrinsic, unlike the surface here, which cannot go beyond. We can make it intrinsic, can't go beyond intrinsic. The metallurgical junction is always intrinsic. The external bias changes from conducting to non-conducting, depending upon whether we're in forward or reverse bias. That's the principle of rectification, and inversion is not applicable. In an MOS, it can be a barrier or a not barrier, depending only on the external bias. A barrier is created if it's not there. If it's there in equilibrium, we can obliterate it by going into accumulation. The silicon surface can be anything we want. It can be intrinsic, it can be conductive, and it can be non-conductive. It can be non-conductive if it's in depletion. It can be conductive if it's in accumulation, or if it's in inversion. The external bias effect on the junction at the the external effect on the junction. What I mean here, and I should have explained this back here, this refers to the conduction from the silicon to the metal, conduction from the N to the P, from right to left. Here, there is never conduction across the barrier, simply because we have this oxide. Oxide is non-conductive. Doesn't matter what the external bias is, we get no conduction from the silicon to the metal. The conduction is on the silicon surface from, we'll see, from what we call the source to the drain, but there is no conduction between the silicon and the metal. So that's why we say it's always non-conductive. Inversion, not possible, not applicable, always possible. We simply make the bias on the gate such that we get an inversion. If it is P silicon, we make the gate positive. If it is N silicon, to get inversion, we make the gate negative. Now let's take a look at some problems, and I picked two problems from chapter 19, which is the chapter on worked problems, and let's get started because I think they illustrate some interesting concepts. Okay, so this is problem 19.1. Looks like a typical capacitance voltage plot or CV plot. A little bit different here because we're given the cross-sectional area of the gate oxide, and we're told that it's 100 microns by 100 microns. So instead of being the areal capacitance measured in farads per square centimeter, this is the total capacitance. And the first question we might want to ask, even before we look at the problem statement, is this a NMOS, which is P-type silicon, or a PMOS, N-type silicon? Well, from the shape, and this is the giveaway, the shape of this region here and the rather sharp rise in the capacitance, I would say this is the flat band voltage, this is the depletion region, and this is the threshold voltage. So this would be accumulation, this would be depletion. Somewhere in this region there is intrinsic, where the intrinsic level crosses the Fermi level. So this would be weak inversion, and then here we'd have strong inversion. And no, that's not a mistake. I didn't mess up on the line here. The line actually does slope down, and we want to take a look at that. So this is the problem statement. They ask for the thickness of the gate oxide. Do we have a metal gate or a polysilicon gate? And that's what we want to talk about a little bit. Is the substrate N-type or P-type? That's fairly straightforward from the shape. Estimate the flat band voltage and the threshold voltage. Again, we just read them off. What is the work function of the gate electrode? And then we'll see how we figure that out simply from the plot. And what else? Oh, is the substrate lightly doped or heavily doped? I think lightly doped is a little bit of a misnomer here. Lightly doped, and I'm going to change that. This would be less than 10 to the 17th, 10 to the 18th. That would be 10 to the 18th would be heavily doped. And is the measurement frequency high or low? And that should be fairly straightforward. Okay. The easiest part to answer is it N-type or P-type? Well, because we have accumulation on the left, inversion on the right, it must be P-type silicon or NMOS. What's the flat band voltage? Minus 0.7 volts. What is the threshold voltage? Plus 0.25 volts. So those are fairly straightforward. Also quite straightforward is the calculation to figure out what the thickness of the gate oxide. This is the easiest region in accumulation. So the C-ox in accumulation is 70 picofarads, and we just put that into our formula. 70 picofarads, 10 to the minus 12 means pico, and that is the oxide permittivity multiplied by the cross-sectional area divided by the oxide thickness, which is what we're trying to find. The 4 here is the relative permittivity of oxide. This is the permittivity of free space. The cross-sectional area is 100 microns, which is 100 times 10 to the minus 4th centimeters. That is squared. And we just basically put the T-ox upstairs, the C-oxide downstairs, and we get that it is 50 angstroms for the T-oxide, which is a little bit on the high side for a modern device, but it's still pretty reasonable. Now we take a look at part B. We've already done C and D. That's pretty cool. Does the capacitance have a metal gate or a poly gate? Well, here is the issue here. Let's assume it has a poly gate. And what we have, and this is redrawn the rather crude schematic, we have the gate here, and I'm going to claim that this is not metal but polysilicon, and if it is polysilicon, it is N plus or N plus plus. It is degenerately doped generally, which means that there are positive ions that are generally covered up by the sea of negative electrons if it's N plus plus. However, when I put a heavy positive voltage on the gate, like in inversion, which is this region here, then all I need is to have the sufficient number of positive whatever on this side of the oxide to counterbalance the electrons on the oxide silicon interface. And I say whatever because they could be holes, which are mobile, or they can be uncovered fixed ions. So if we subject this thing to a heavy positive voltage, we can at least have the possibility of having silicon depletion, which will uncover some fixed ions. In that case, we have essentially a tiny layer, a very, very thin layer. I'm going to claim it is on the left side of the gate because mobile holes will always rush to be as close to the negative electrons as they can be. So we're going to have a tiny depleted layer here. However, that will add a capacitance. It will be a very large capacitance, but it will be enough to drag down the overall capacitance of the structure, because you know that capacitors in series add like resistors in parallel. So even a very large capacitance here will be enough to reduce the overall capacitance. And that is why we have this negative slope to the capacitance line. As the inversion voltage, the gate voltage and inversion gets bigger and bigger, this depletion region will go from perhaps 2 angstroms, 3 angstroms, maybe 4 angstroms, and it will drag down the total capacitance. So that's why we say that this particular capacitor has a polysilicon gate, and it is an N plus polysilicon gate. So, given the fact that we conjecture, and I think we should be fairly confident, that this is a degenerately doped polysilicon gate, therefore it must be that the work function of the gate electrode is essentially the affinity of silicon, which is about 4 electron volts. Therefore, we can write that the flat band voltage minus 0.7 volts right here is equal to the difference in the work functions. The metal work function is 4.05. So we put these numbers into this relatively straightforward equation here. We find that phi sub s is not really what we'd expect it to be. It's only less than 0.2 eV below mid-gap. That is a really, really lightly doped. We would expect it to be 0.4 or more eV below mid-gap. We are generally used to saying flat band voltages not minus 0.7 volts, but rather minus 1 volt. In fact, many of the examples that we have been doing until this time have had flat band voltages of about minus 1 volt. So that means that this phi sub s is a little bit unusual, and it is lightly doped, probably in the range of 10 to the 15th, or maybe even less. So that answers part. What part is that? Oh, yes, part F. And finally is the measurement frequency high or low. If it was a high frequency, we would have a depletion region which kept going because it jumps up rather dramatically at the threshold. This measurement is done at a low frequency. Okay, I think we've answered all of them. All right, so let's go on to the next one, which is a little bit more interesting. Yeah, so let's give it a shot. Let's take a look at the picture. Wow, that's a little bit different picture than we had before. That certainly doesn't look like a CV plot. So we expect this is not going to be capacitance. In fact, it is charge. Now, how do we know this is accumulation and how do we know this is inversion? Because we're told it is a p-type silicon. Therefore, the accumulation will be on the left and the inversion will be on the right. And in the middle, there will be depletion. Okay, so they want to know what's the oxide thickness. Again, let's do the same thing that we did in the previous problem. Look at the accumulation part, and let's see how that goes. So, in accumulation, we have a simple parallel plate capacitor. The charge is equal to Cox divided by the voltage across the oxide. So we can read off any point. We can just take, say, -1 volt, and then we have a Q surface charge of 4 times 10 to the -7th. Fairly straightforward. We know Cox. This gives us an areal capacitance in farads per square centimeter, and we find that the Tox, exactly the same calculation, is about 88 angstroms. A little bit on the thick side, but not too unreasonable. Okay, let's look at B. What is the doping concentration? Oh, that's not that trivial. So now we have to put our thinking caps on and figure out, first of all, which region are we going to look at. This is a good region right here in depletion, because in inversion, we're again talking about oxide capacitance. This is where we have a situation where we have a depletion capacitance and an oxide capacitance. So that's the area we're going to be one to concentrate on. And we'll, of course, want to pick a point. Well, a nice point to pick would be the threshold right here, because we know the voltage and we know the charge. So that's a good thing. And at threshold, I could say VT or VTH. You'll find both of those formulations. The band bending is equal to 2πb, which you've seen many, many times. So we know that the threshold is 1 volt. We know also, I believe, that the, are we told here? Yeah, okay. We're told that the Vg minus VFB is equal to minus 1 volt. So we just put that in. We let the flat band voltage be equal to 0. We use our basic equation relating the πB, the bulk potential, to the doping. We know this is P, so I probably could have put in NA rather than just N. This is what we're trying to find. Of course, we know Ni is 10 to the 10th, and we know πB. We're going to put all that stuff into our formula for Vox, which is sitting right here. We know Vox. It's given. Where is it? Vox is right here. Minus 8. Yeah, not plus 8. Okay. So we put all that good stuff in here. 2 times 2, that's where we get the 4. It's silicon, so this is all of this stuff right here is 10 to the minus 12th, and we are looking for N. What we do first is shift out the N and we look at the rest of the stuff. And that's what we're doing here. We know Cox we found in part A. So all of this stuff here, excluding the N, is 2.1 times 10 to the minus 9th. Now, we go back to this point right here, where we've done all the constants. We don't know N, and that is a problem, and we're going to have to use an iterative solution which satisfies this equation. So the first thing we do is we try 10 to the 16th. We try a acceptor doping of 10 to the 16th, and if that's true, then our bulk potential will be 0.36 eV. When we 10 to the 17th, it's 0.42. This is 60 millivolts less than 0.36, and we see, if indeed 1 volt is equal to all of this when we put in 10 to the 16th here. So we do that. This is why it's 10 to the 8th, because we've already taken out the square root. The square root of 10 to the 16th is 10 to the 8th. So we have, the only thing we don't have is the bulk potential square root. So it is 2 times 5b. So 5b is 0.36, 2 times 5b is 0.72. That's the square root, and this is the 2 times 5b over here. That's why we have 0.72, and we find that all the stuff on the right side is 0.9, which is less than 1 volt. Close, but not quite. What do we have to do? We have to juice this guy up. And in order to juice this guy up, what do? We increase the doping, which will increase the bulk potential, and we're going to get a bigger number on the right side. And again, we can choose any number we want. We don't want to go like overboard. We don't want to go to like 10 to the 18th or something like that. Let's do a moderate increase from 10 to the 16th to 5 times 10 to the 16th. And then we have a 5B of about 0.4 volts. And we put all that stuff in, and we get a number which is a little bit greater than 1 on the right side. Makes sense? So it says to me that we're, in this case, a little too high. Too low over here, too high over here. Split the difference about 2 times 10 to the 16th. And we can see if that's reasonable by putting in a number which we know is too high, namely 10 to 10 to the 17th. And at 10 to the 17th, we get a number which is much higher. So this is probably a pretty good number. The true doping is somewhere in the range of 2 times 10 to the 16th. I have an alternative solution to this. You can go over it. In the interest of time, I don't think I want to spend too much time on that. We get the same answer, which is, that's a good thing. Okay, Part C is, we say that when VG minus VFB is minus 1 volt, what are we asked to do in Part C? Must be something here. We want to find the voltage drop across the oxide. So when the gate voltage is at this point, we want to find the voltage drop across the oxide. Relatively straightforward. Where is it? Right here. Clearly the device is accumulation. It's on the left side of the graph. There's no band bending, and there's no voltage drop across the silicon. So we can write immediately that this is, I generally say phi here. I unfortunately included the S here, but there's no band bending in the silicon, and therefore the voltage is completely across the oxide, and it is minus 1 volt. And finally, Part D. And you'll excuse me, I'm going to have to go back to the plot here to explain this a little bit more detail. we want to know what, oh, it must be here somewhere. Okay, find the band bending in the silicon when Vg minus VFB is plus 0.5 volts. And that would be right about here, about 0.5 volts. So we want to know what the band bending. Why is there band bending? Well, because it's in depletion. So let's do that. Back over to here. We have an oxide voltage across the oxide given by this term plus the band bending, and unfortunately I apologize for leaving the putting the S in here, but phi or phi sub S, it's the same thing. It's just band bending in the silicon. Generally, people will use phi sub S when they talk about the band bending at the surface. I like phi because it's total band bending, and it can be generally either in the surface or away from the surface. Okay, so this is the voltage across the oxide. We know actually everything here, and this is what we're trying to find, because we know the doping is 10 to the 16th. The way the problem is set up, it's a good way to do it, is it leads you. It goes from part A to B to C to D. If we didn't know the doping, we would be in some distress here. We wouldn't know what to put in for here, but because we already solved for that, we can put in that the doping is 10 to the 16th, and the only thing we're trying to find is phi sub S. So it's one equation and one unknown. We know the C ox, which we found in part A, is 4 times 10 to the minus 7th. So we substitute all that good stuff in, and we get a quadratic equation in the square root of phi, and we solve and we find that phi, or in this case I say phi sub S, is 0.38 eV, which is a very reasonable number. Just one more little note on here. We found the band bending is 0.38. What does that correspond to in doping? Well, if it was 0.36, the doping would be 10 to the 16th. So it's a little bit more doping than 10 to the 16th. How about 2 times 10 to the 16th, which of course is exactly what we found back in part C. So really, I could have read this off immediately and said, you know what, since the doping is 10 to the 16th, or 2 times 10 to the 16th, the band bending should be at threshold about 0.38 or 0.39. So all that makes a lot of sense. Okay, so now let's look at some corrections to the simple model. We'll just get started here. We'll continue this in our next session. The idea is here, up to this point, we've done energy band diagrams and the different regions, accumulation, depletion, weak and strong inversions, but we haven't said what the surface charge is, specifically in weak and strong inversion. So now we're going to be looking at the amount of charge that we have at the surface. Now, we have an expression for the inversion charge, the amount of charge at the oxide-silicon interface in strong inversion, and that is our simple theory. It's just a parallel plate capacitor, and the amount of charge at the surface would be C oxide, which is an aerial. If it's an aerial capacitance, this would be a surface charge, and it's just multiplied by the voltage above threshold. So at threshold, there is, according to this theory, there should be no inversion charge. And of course, that is absolutely not right. Okay, so that's our object in this section, and this is basically the entire chapter 8. It's got a fair amount of mathematics, but we'll deal with it, no big deal. So let's look at the energy band diagram. We have, of course, have the gate, the oxide and the silicon. And in this particular case, we happen to be intrinsic, so clearly the simple theory says there is no charge, but I'm going to claim that as we increase the gate voltage, there starts to be some charge here. And if there is charge here, we want to know, is that charge distributed uniformly from the source end to the drain end? And what are we talking about here? This is the source end on the bottom. This is the drain end on the top. So basically, we've taken this figure and we've rotated it 90 degrees clockwise. Now, here's the difference, or here's the new issue here. I'm going to claim, and we're going to show this, that the amount of surface charge, or inversion charge, or charge at the surface in weak inversion is going to be different at the source end and at the drain end. And that is absolutely critical to the way a field effect transistor works. Because we have different amounts of charge at the two ends, we're going to have different energy band diagrams depending on the place where we make the cut. So I'm going to be making the cut, for example, somewhere in the middle, and I'm going to say this is what the energy band diagram looks like if we cut the structure at point A. It will be different than if we cut the structure over here, and then if we cut the structure over here. So that is kind of an introduction to what we'll be doing. Again, we have the bulk band bending is 0, and the band bending at the surface in this particular case will be 0.42 eV, corresponding to a doping of 10 to the 17th. So let's stop here, and we're going to have to skip. Oh my goodness, we're going to have to skip so much. In fact, I'm going to stop it and go right down to the... So next time we'll pick up this discussion, and we'll look at the corrections to the simple model in a quantitative sense, and that's going to take a fair amount of effort, as I say, but we'll deal with it, and I hope it'll be really, really interesting. We'll end our session with a very powerful scene from The Grapes of Wrath. This could be right out of today's headline. The book was written, I believe, in 1939, 1940 time frame, John Steinbeck. The movie, I believe, was 41 or 42. But as I say, this scene could be literally taken from today's headlines, and we'll see you next time.
Mentions lately, Bill?
Well, this one ain't bad. A little kid comes late for school, and the teacher says,
Jesus.
Could you see your way clear to sell us a loaf of bread, ma'am?
This ain't a grocery store. We got bread to make sandwiches with.
I know, ma'am. Only it's for an old lady. No teeth. Got to soften it with water so she can chew it. And she's hungry.
Why don't you buy a sandwich? We got nice sandwiches.
Well, I sure would like to do that, ma'am. But the fact is, we ain't got but a dime for it. It's all figured out. I mean, for the trip.
You can't buy no loaf of bread for a dime. We only got 15-cent loaves.
Give 'em the bread.
We'll run out before the bread truck comes.
All right, then we run out.
This here's a 15-cent loaf.
Well, could you see your way to cutting off 10 cents worth?
Give 'em the loaf.
No, sir. We want to buy 10 cents worth, that's all.
Go on, it's yesterday's bread.
Go ahead. Bert says to take it.
Well, it may sound funny being so tight, but we got 1,000 miles to go, and we don't know if we'll make it. them penny candies, ma'am?
Which ones?
There, them stripy ones.
Oh, them. Well, no. Them's 2 for a penny.
Give us 2 then, ma'am. Go on, take 'em, take 'em. Thank you, ma'am.
Them ain't 2 for a cent candy.
What's it to you?
Them's a nickel apiece candy.
We better get going. We're dropping time.
Now, so long.
Hey, wait a minute. You got change coming.
What's it to you?